Welcome to this course on computational mathematics with Sage Math. Now, remaining part of this course, we will be looking at solving linear programming problems using Sage Math. So let us get started. First of all, let us recall a generic optimization problem can be defined as follows. Maximize or minimize a function z, which is a function of n variables, let us say x1, x2, xn. We call them as design variables. Subjected to certain constraints, we can consider two types of constraints. One is less than equal to constraints, and other one is equality constraints. So there are m inequality constraints, g1, g2, gm, and p equality constraints, h1 equal to 0, h2 equal to 0, hp equal to 0. Here f, gi and hj's are real valued functions of n variables x1, x2, xn. In this case, this function z is equal to f of x1, x2, xn is called the objective function, and this g1 to gm and h1 to hp, they are called constraints. So this is what is called constraint optimization problem. So this is a generic optimization problem. Now, what is a linear programming problem? Linear programming problems are special types of optimization problem in which this objective function, that is z equal to f of x1, x2, xn, as well as all the constraints gi's and hj's are linear. We have seen what do we mean by saying a linear function on n variables x1, x2, xn. Any linear function f from Rn to R, it looks like some c1 times x1 plus c2 times x2 plus cn times xn. We have seen that in linear algebra course. Okay, so that is what is called a linear programming problem. It is a special type of constraint optimization problem in which objective function as well as all the constraints are linear. Now, let us first take some examples and then we will see how we can formulate these problems. These linear programming problems have lots of examples, have lots of applications in real life and also in industry. Let us look at a few problems and then we will also look at how to formulate these problems in terms of a linear programming problem. So first problem is as follows. A manufacturer produces four types of products, x1, x2, x3 and x4, and there are three inputs to this production process. What are they? Labor in man weeks, kilogram of raw material A and boxes of raw material B. Now the requirements for this production are given in this table. So there are four inputs, that is the inputs are three types: man weeks, kilogram of raw material A and boxes of raw material B, and the four types of products are x1, x2, x3, x4, and the x1 requires 1 man week and 6 kilogram of raw material A and 3 boxes of raw material B. Similarly, x2 requires 2 man weeks, 5 kilogram of raw material A and 4 boxes of B, and so on. And the total number of man weeks available for this is 20 weeks. The total number of raw material A available for this production process is 100, and number of boxes B available is 70. Let us assume that the small x1 unit of capital X1 and small x2 units of capital X2, small x3 units of capital X3, and small x4 units of capital X4 are produced. Now the question is to find how many units of x1, x2, x3, x4 are to be produced in order to maximize the profit. So in this case, the one unit of capital X1 sells at $6, one unit of capital X2 sells at $4, and one unit of capital X3 sells at $7, and one unit of capital X1 sells at $5. The problem is, as I said, is to maximize the total revenue. Now what will be the total revenue? If you look at this table, the total revenue for X1 unit of capital X1 is going to be 6 times X1. For capital X2 it will be 4 times X2. For capital X3 it will be 7 times X3, and for capital X4 it will be 5 times X4. Therefore total revenue for this is going to be 6x1 plus 4x2 plus 7x3 plus 5x4. This is what we need to maximize. Now there are constraints. What are the constraints? The constraints are in terms of availability of these manufacturing inputs, namely man weeks, kilogram of raw material A, boxes of raw material B. So if you look at the first one, the man weeks available total is 20. So the man weeks required for x1, x2, x3, x4 is going to be x1 plus 2x2 plus x3 plus 2x4, and that should be less than equal to 20. That is the first constraint. Similarly, for material A, for kilogram of material A, the total used in producing x1, x2, x3, x4 units of capital X1, capital X2, capital X3, capital X4 is going to be 6x1 plus 5x2 plus 3x3 plus 2x4, and that should be less than equal to 100. That is the second constraint. Similarly, you have the third constraint, that is for number of boxes of raw material B. So these are the three constraints. So therefore, and this x1, x2, x3, x4, we will assume that they are all non-negative. Of course, in this case, the number of boxes will be an integer. However, we will assume that they are all real numbers. Similarly, man weeks we will assume to be non-negative real numbers. So this is how we can formulate this problem, and this is what is called a linear programming problem. So you have the problem is of maximization type, that's the objective function, and there are three constraints in 4 variables. Now this problem you can also write in matrix notation. For example, this 6x1 plus 4x2 plus 7x3 plus 5x4, I can write this as C transpose X, where C is going to be a column vector, C1, C2, C3, C4. Here C1 is 6, C2 is 4, C3 is 7, and C4 is 5. And X will be column vectors x1, x2, x3, x4. Subjected to these constraints, this constraint again the left hand side we can write in terms of A times X, where A is going to be this matrix, which first row is 1, 2, 1, 2, second row is 6, 5, 3, 2, third row is 3, 4, 9, 2, and right hand side is, we will denote it by B, which is the column vector 20, 100, 75, right. So that is, and X is greater than equal to 0 is same as saying x1, x2, x3, x4 all are non-negative. So that is how this problem can be written in terms of matrix notation, or you may say this is in compact form, right. Let us look at another example. A chemical manufacturing company produces 3 types of chemicals, capital X, capital Y, capital Z. These chemicals are produced using 2 different processes, capital P1 and capital P2. It is given that running process P1, capital P1, costs $6 per hour, and it yields 3 units of chemical X, 1 unit of chemical Y, and 1 unit of chemical Z. Similarly, running process P2 costs $6 per hour and it produces 1 unit of capital X, 2 units of capital Y, 1 unit of capital Z. And to meet the customer demand, one has to have at least 10 units of chemical X, 6 units of chemical Y, and 4 units of chemical Z. Okay, the problem is to minimize the cost of production. So here the previous problem was to maximize the revenue. In this case, we want to minimize the cost of the production. Now, how do we formulate this problem? Let us assume that capital P1, process capital P1 runs for small p1 hours and capital P2 runs for small p2 hours. Now, if it runs for a small p1 and a small p2 hours, the cost is going to be 10 times p1 plus 6 times p2. That is what is to be minimized. This is objective function. Now, if you look at if the capital P1 runs for P1 hours, then and capital P2 runs for P2 hours, the number of units of chemical capital X produced will be 3P1 plus P2, and the total requirement of capital X is at least 10. So this capital 3P1 plus P2 should be greater than equal to 10. Similarly, the second constraint will be P1 plus 2P2 greater than equal to 6, and the third constraint, that is for the third chemical, that should be P1 plus P2 greater than equal to 4. So these three constraints are coming from the number of units that are produced by each of this process P1 and P2. Okay. So this is the problem, which is minimize Z is equal to 10P1 plus 6P2, that's the objective function, subjected to these three constraints, 3P1 plus P2 greater than equal to 10, P1 plus 2P2 greater than equal to 6, and P1 plus P2 greater than equal to 4. Again, this P1 and P2 are non-negative. So again, this also you can write in terms of matrix notation. I will leave this as an exercise for you to work out. Let us look at another very important problem. This is what is called diet problem. And what is it? This says that you have to determine most economical diet that satisfies basic minimum nutritional requirements of a healthy person. Okay. Now, the cost and the nutrition value per unit of different foods are listed in this particular table. Now, there are 6 types of food available, namely bread, milk, cheese, potato, fish, and yogurt. And the cost of each of this food per unit cost is given. And so, and there are also some certain requirements. What is that? The diet must contain at least 250 calories. So total calorie of the diet should be minimum 250 calories. The diet must contain no more than 10 grams of protein. So the protein requirement is less than equal to 10 grams. The diet must contain no less than 8 grams of carbohydrates. So the number of units or the carbohydrates in terms of gram required is at least 8. And similarly, the diet must contain at least 1 unit of fish, and then it must contain at least 2 units of milk. So now let us look at how we can formulate this problem. Now the question is, what are the combination of food that should be consumed so that it minimizes the cost? The cost of each unit of bread, milk, cheese, potato, fish, and yogurt are given here in the first row. For example, 1 unit of milk requires let us say $3, or it could be 3,000, whatever is your unit, maybe 300. Okay, so let us look at how we can formulate this problem. Now the first is the cost of, so first of all let us assume that x1 is the number of units of bread, x2 is number of units of milk, x3 is number of units of cheese, x4 is number of units of potato, x5 is number of units of fishes, and x6 is number of units of yogurt that are required. So in this case, we have to minimize the cost. So the cost that will come from the first row, this is going to be 2x1 plus 3x2 plus 8x3 plus 2x4 plus 11x5 plus 6x6. This is what is to be minimized. So that's your objective function. Now the first constraint, let us look at the first constraint. The first constraint is the number of calories required. The calories required is 250, at least 250. So the total calorie from the last row is going to be 90x1 plus 120x2 plus 106x3 plus 97x4 plus 125x5 plus 180x6, and this should be greater than or equal to 250. That is your first constraint. Similarly, the second constraint is for the requirement of protein, which says that it should be no more than 10 grams of protein. So that the protein requirement that is going to come from the second row. So it will be 4x1 plus 8x2 plus 7x3 plus x4 plus x5 plus 8x5 plus 10x6, and that should be less than or equal to 10. Similarly, you have third constraint for the carbohydrates, and fourth constraint is for fat. And then you are also given that the diet must contain at least 1 unit of fish. So that is x6. So x5. So x5 should be greater than or equal to 1, and the diet must contain at least 2 units of milk. Therefore x6 is greater than or equal to 2. So these two are also constraints, and of course all these x1, x2, x3, x4, x5, x6 are non-negative. So this is what is called a diet problem. Now in actual practice, you may have several types of foods. So this x1 to x6 may become x1 to x20, and similarly different types of nutrients also will be present in the food. So this problem could be much bigger also, right? There are many other types of problems which can be formulated in terms of linear programming problem. I'll just give some of them, and I would leave this for you to explore how we can formulate these problems. So for example, the first problem is transportation problem, where you need to determine a transportation schedule so that we can find the cheapest way of transporting a product from a warehouse situated at different locations to different consumers. That is what is called transportation problem, and this problem is quite important these days. Similarly, warehousing problem. Now again, as I said, nowadays we are living in an era of digital market. For example, Amazon is one of the digital market, right? So when you buy product from Amazon, you will see that it is delivered from some place. So that is where they will have these warehouses. So now how does this Amazon create these warehouses so that they can supply these products efficiently? That's the question. Similarly, you have traveling salesman problem, where let us say there is a traveling salesman, there is a salesman, and he is being given some set of cities to kind of promote certain product. He lives in some city, and the question is how should he visit all these cities? He has to visit all the cities at least once, and not more than once, and then he has to come back to the place where he lives. Okay, so how to formulate this traveling salesman problems? Similarly, you have knapsack problem. Think of let us say you are going for some kind of let us say trekking, and then you have certain bag which you have to carry, and then certain items you want to carry. Each item will have certain value in terms of your satisfaction level or in terms of survival and things like that. So the question is, what are the items you should carry in your bag so that you get the maximum value? Of course, you can't carry everything because there is a maximum load that you can carry. So that is what is called knapsack problem.
Then you have cutting stock problem, where in the industry this is very important. You have generally industry will get big sheet of let us say metal, and from which they have to cut in small pieces, that each piece will have certain requirement. Let us say the requirement is, let us say, 10 inch, 8 inch, 9 inch width, and that they have to cut. And then of course there will be requirement how many of 10 inch sheet is required, how many of 8 inch sheets are required, and things like that. So this is what is called cutting stock problem. This is again very important class of optimization problem, linear programming problem. You also have job scheduling problem, where you can think of for example, let us say flight crew scheduling, or scheduling of certain job which can go through many different machines. So these are called job scheduling problems. There are a host of linear programming problems that you can come across. We come across linear programming problem almost every day in our daily life, not just in industry. Okay. So I request all of you to just explore these problems and see how will you formulate. Next, let us look at, so we have already seen several linear programming problems. Some of them were minimization type, some of them were maximization type, some of them involves some constraints are greater than equal to, some constraints are less than equal to. You can also have some equality constraints. So what we will be looking at a linear programming problem in standard form, and that will be of minimization type, which will be C transpose X, which is going to be, let us assume that X is X1, X2, X and N variables. So this will be C1, X1 plus C2, X2 plus ... Cn, Xn. That is to be minimized and subjected to constraints. We will be considering all equality constraints. So that equality constraints, let us say there are M equality constraints that we can represent by Ax equal to B. And we will also assume that X is non-negative. That means all design variables are non-negative real numbers, and also this right hand side of this Ax equal to B are also non-negative. So this will be our requirement. One more requirement we will have, that number of constraints is less than equal to number of variables, because in case you have more constraints than the number of variables, it is possible that it may not have a solution. So we will assume that number of constraints is less than equal to number of variables, and also we will assume that this matrix A is full rank matrix. That means since M is less than equal to N, the rank of A will be, maximum rank of A can be M, and that is what we will assume. So this we will call as standard linear programming problem. What is it? It is of minimization type. It is subjected to equality constraints, where all the right hand sides are non-negative and all design variables x1, x2, xn are greater than equal to 0, and also the A is full rank matrix. So this is going to be the assumption. Now as I said earlier, this first fx, this is what is called objective function or cost function, and this Ax equal to B, x greater than equal to 0, this is called constraint. Therefore, if you define set of all x in Rn, that is x1, x2, xn in Rn, which satisfy these constraints, that is Ax equal to B and x greater than equal to 0, this, let us denote this by omega, then this is what is called constraint or feasible set. So our actually aim is going to be study this feasible set. That means find all these points which satisfy this feasible satisfy these constraints, and that minimizes the objective function. That is what is going to be the way to solve this problem. Okay. Now we have considered this as a standard linear programming problem, but then we saw just now that our linear programming problem need not be of this type. So if you have any linear programming problem, actually you can convert this into standard linear programming problem. How do we do that? So let us look at what are the steps
which are required in order to convert any linear programming problem into standard form. The first is objective function could be of maximization type. If it is minimization type, fine. But if it is maximization type, you can minimize minus of the objective function, right? Because maximization of f is same as minimization of minus f and vice versa. Therefore, if the objective function is of maximization type, then you minimize minus of f. Second, suppose any of this right hand side, that is b1, b2, bm, is negative, then that particular equation you multiply by -1, so the right hand side will become positive, and of course inequality will also change. If it is less than equal to, it will become greater than equal to. If it is equality, it will remain as it is. Similarly, if you look at the inequalities, inequality constraints have to be converted into equality constraint. Now there are two types of inequality that are possible. One is less than equal to, other one is greater than equal to. So in case any of this constraint is of less than equal to type, let us say kth constraint is less than equal to. That means what is the kth constraint? It will be summation aki xi. This should be xi here. This is a mistake. Let me correct this here. This is xi here also. Xi. Right. So if this is less than equal to constraint, then what you need to do is you need to the left hand side is less than equal to the right hand side. Therefore, you need to add some non-negative quantity. So that we will call as, let us say, sk, and that is called slack variable, which will be non-negative variable. Similarly, in case any of this, one of these equation, let us say jth equation, jth constraint is greater than equal to, again here there is a typo, here this should be xi, and similarly here also xi. Okay, so if it is greater than equal to inequality, let us say jth inequality is greater than equal to type, then you need to subtract something non-negative from the left hand side, and that let us denote it by sj, and that we call as surplus variable, because it is a surplus. On the left hand side it is surplus, so you need to subtract something in order to make it equality. Right, so that constraint will be converted into summation aji xi minus sj is equal to bj. Now by doing this, we have converted all the less than equal to, greater than equal to into equality. But it's also possible that some design variables, see, our requirement is all the design variables x1, x2, xn should be non-negative. So in case any of this design variable is, let us say, unrestricted, it can take any value, positive or negative. That means it takes a real value. In that case, what you can do, let us say xk is unrestricted. Then xk can be written as difference of two non-negative variables. So xk can be written as xk dash minus xk double dash, where xk dash and xk double dash both are non-negative. For example, if it is -4, I can write -4 as let us say 3 minus 7, right? Okay, so these are the steps using which any linear programming problem can be converted into standard linear programming problem. Okay, now let us look at a small example. So in this case, the problem is to maximize z is equal to 9x1 plus 8x2 subjected to these constraints x1 minus 2x2 greater than equal to 3, 3x1 minus 4x2 less than equal to 5, and 6x1 minus 7x2 is equal to 8. And here x1 is unrestricted, it can take any real value, and x2 is non-negative. Now how do we convert this into a standard linear programming problem? So first let us look at these design variables x1 and x2. Here x1 is unrestricted, so we will write x1 as, let us say, y1 minus y2, where y1 and y2 are non-negative. So everywhere wherever you have x1, you replace it by y1 minus y2, and this x2 is non-negative, so we don't need to change anything. However, since I have written x1 as y1 y2, x2 we will also write as y3, so we will be dealing with variables now y1 y2 y3, they are all non-negative. So that is the first thing we need to do. And now let us look at the problem is of maximization type. Therefore, we need to minimize negative of this z. So you have to say minimize minus z, which is equal to minus 9 times y1 plus 9 times y2 minus 8 times y3. Okay, that is the objective function. Now look at the first constraint. The first constraint is greater than equal to type. So we'll need to subtract a surplus variable, and let us call that variable as y4. So the constraint, first constraint, will get converted into a y1 minus y2, which is in place of x1, minus 2y3 minus y4 is equal to 3. Similarly, the second constraint is less than equal to type, so that you have to add a slack variable, so that will become 3 times y1 minus 3 times y2 minus 4 times y3 plus y5, that is the slack variable. This is equal to 5, and the third constraint is already equality type, so we do not need to do anything. It will be simply 6y1 minus 6y2 minus 7y3 is equal to 8, and here now you have y1, y2, y3, y4, y5 all non-negative. Okay, so this is how we have converted this linear programming problem into standard form. Like this, any linear programming problem can be converted into standard form. Okay, now let us look at, let me just tell you very basic history of linear programming problem. Actually, this is not very old. First efficient method of solving linear programming problem was given by Kantorowicz in 1930s, and he presented actually a number of solutions of some of the linear programming problems related to production and transportation problems. Similarly, during the Second World War, actually the main development or considerable amount of development in solving this linear programming problem was made during Second World War. So during Second World War, Koopmans contributed significantly to solution of transportation problem, and Kantorowicz and Koopman, these two people were given Nobel Prizes in 1975 for their work. In 1947, Dan Jigg developed a new method which is called simplex method, and that is what this simplex method is we are going to concentrate a lot. We are going to study this in more detail. So he developed simplex method for solving linear programming problem. That was in 1947. However, this simplex method has exponential worst case complexity. What does it mean? It means that if you increase the number of design variables, the time taken to solve linear programming problem will increase multifold. There will be exponential increase. That is what it means by saying this method has exponential worst case complexity. In 1979, Kachyan developed an algorithm, and that had polynomial complexity. Even in 1984, Karmakar proposed a new algorithm that has polynomial complexity, and it appears to solve some of the complicated real-world linear programming problem more efficiently than simplex method. Of course, if you want, you can look at more detailed history of linear programming problem. This is very briefly I have told you. Right. Now, there are different types of linear programming problem depending upon the nature of design variables. So in case all the design variables are real, we call them as real linear programming problem. In case the design variables are all integers, for example, traveling salesman problem or knapsack problem can be thought of as integer linear programming problem. Then you can also have 0-1 problem where the design variables can take value 0 or 1. So such problems are called binary linear programming problem or 0-1 linear programming problem. For example, the knapsack problem, if you have n items to choose from, either you choose or you don't choose. So if you choose, you can take that as 1. If you don't choose, you can take that as 0. So that can be thought of as 0-1 linear programming problem. But in some cases, you can have mixed integer programming problem where you have some design variable which can take integer value and some design variable can take real value. Right. So these are different types of linear programming problem. We are going to concentrate mainly on solving real linear programming problem. Of course, towards the end, I will also tell you how one can solve integer linear programming problem using SAES-Math. Right. Now, in SAES-Math, in order to solve linear programming problems, we are going to use two types of function. One is interactive LP problem, which is going to be more of pedagogical purpose, and the second one is mixed integer linear program. So these are two inbuilt facilities in SAES-Math using which we will be solving linear programming problem. And these are some references you can look at. So first one is a book on linear and non-linear programming by David G. Leuenberger. This is Springer publication. There is another book on operation research by H.A. Taha, and this is, the title is Operation Research and Introduction. This is published by Pearson. So actually these linear programming problems are studied in a branch called Operation Research. That is a very important branch of mathematics where we study these linear programming problems. And you can also look at another book on Operation Research, Principles and Applications by G. Srinivasan from IIT Madras, and this is published by Prentice Hall of India Learning Private Limited. You can also refer to two NPTEL lectures, one by again Professor G. Srinivasan on fundamentals of operation research. This is the link available, and there is another one, Operation Research by Professor Kusum Deep from IIT Roorkee. She is from IIT Roorkee. So these two are the courses. If you want to study these subject on operation research in more detail, you can go through these courses. Let me leave you with one simple exercise, which is to convert this linear programming problem into standard form, that is minimization type and subjected to equality constraint with all design variables non-negative. And as I said, please also look at how to formulate this job scheduling problem, traveling salesman problem, cutting stock problem, and knapsack problem. So thank you very much, and in the next class we are going to look at how to solve linear programming problem using graphical method. So whenever you have a problem which involves only two variables, those problems, and of course if it is a reasonably small problem, can be solved using graphical method. So that we will look at in the next lecture. Thank you very much.